Alright, welcome back everybody. In this video we're going to look at the last two examples from the polar to Cartesian conversions lesson. We'll start here with example 2. We're going to convert x squared plus the quantity y minus 3 squared equals 9 into polar form. The first thing I'm going to do in order to help me do this is I'm going to expand out the quantity y minus 3, which gives me y squared minus 6y plus 9. And then I'm going to subtract 9 from both sides. We get x squared plus y squared minus 6y equals 0. We know that x squared plus y squared is r squared. And we know that y is r sine of theta. So this turns into r squared minus 6r sine of theta equals 0. But we can come up with an even better Cartesian equation for this here. If we factor an r out, we've got r times the quantity r minus 6 sine of theta equals 0. And from the zero product property, one of these two things has to be equal to 0, either r equals 0 or r minus 6 sine of theta equals 0. And this is really pretty trivial. At some point in time on this other curve, we'll end up with a radius of 0. So we're going to ignore this one and solve this one for r. And we get that the polar equation that represents this Cartesian equation is r equals 6 sine of theta. Now you should realize from your experience with Cartesian equations that this is a circle with a radius of 3 that has center at point 0, 3. And if we look at this polar equation, r equals 6 sine of theta, I think that's good enough for my window. We should end up with a circle. And of course there's screen distortion on this, so I'll zoom square. Should end up with a circle. That center is at the point 0, 3, and that has a radius of 3. And that's what we see on our graph. Cool. And in this case, the polar equation is significantly simpler than the Cartesian equation, in my opinion. Alright. Example 3, convert the following from polar form into Cartesian form. We'll go the other direction here. Instead of Cartesian to polar, we'll go polar to Cartesian. So r squared is equal to x squared plus y squared. And r cosine of theta is equal to x. And so there's a Cartesian equation that represents this polar equation. And we'll do the same kind of thing in part B. I'm going to multiply both sides by the quantity 2 cosine of theta minus sine of theta. And then this is 2r cosine of theta minus r sine of theta equals 4. And let's see, r cosine of theta is equal to x. R sine of theta is equal to y. And this is actually the equation y equals 2x minus 4. So it should be a line with a slope of 2 and a y-intercept of negative 4. If we take a look, I'm curious to show you this. If we take a look, if we go ahead and graph this, we've got 4 over the quantity 2 cosine of theta minus sine of theta. And if I look at the graph of this, see how it forms that line? Now, it doesn't form it in the order that we're used to seeing it formed. If I put a tracer on this, and I'll even slow down my time step a little bit. Let's see, let's make this pi over 300. It's pretty small. You'll see how this graphs this line. Maybe pi over 300 was a little bit of overkill. Let's go back and make that pi over 60 instead. And it'll graph that line, and you'll see it'll speed up, and then it jumps back over. But it still creates that line. Alright, that's the end of this video. And notice when we're going to 2 pi, it even traces over the line again. That's the end of this video and the end of this lesson on polar to Cartesian conversions. See you guys next time. Have a great rest of your day.